All right, hello. Welcome to CS360 in spring 2021. Um, so this will be an online class. The primary source of content will actually be the lecture notes that I'm writing and that I will be posting regularly, around 2 per week. Um, so these videos, I'll make them occasionally to you know, as an additional resource to kind of explain some things that are better explained through video. Um, but the videos won't cover all the material that is in the notes. So do read the notes to kind of get a full coverage of you know uh, everything in the class. Um, so I mentioned on the course outline and the course website, you can find some additional resources such as um, the 2 optional textbooks that you can use that kind of cover the same material. And they go into a bit more detail and explanation, and also the lecture notes by John Waters that he made for his offering of CS360. So they're also very well written, and they cover mostly the same material. So a few differences. So only the notes that I'm writing and I'm posting are going to be required. But these other resources are kind of available to you. And I should also note my notes tend to be somewhat dense and compact. So that can save you reading time in one sense, and that if you're looking for something specific in the notes, there's often less reading in my version uh, because it is more terse. But on the other hand, sometimes you may wish to see more explanation, and so some of these other resources can help there. If something is if it, the density of my version is confusing. That's also partly why I'm posting these videos, to help kind of explain things a little bit more at length. Although we won't cover nearly everything that's in the notes. Okay, so to start with, let's just get right to the content. So, in this course, we're going to be studying, essentially the point of the course is to study kind of computational models and the mathematical versions of them. So we're sort of introducing the mathematical theory of computation and how to think about computing from a mathematical perspective, how to prove things about it, how to even define it. And so actually most of this, more than half of this course is, or maybe around half, is just going to be building up to the sort of right definition of computing by going through several weaker definitions that don't fully capture the notion of computing as we're used to. So, however, these weaker definitions turned out to capture pretty interesting models, even though they're not kind of the full computer model of computation that we're used to. So they don't quite correspond to modern computers, these weaker notions, but they kind of come up in that many times you actually want to know that this task that you were given can be computed on this simpler machine rather than on a full computer. So in order to define this model and to kind of introduce it and talk about its properties, or these models rather, we will start with talking about languages. In mathematics, a language is going to basically mean a set of strings, a set of a string, as you know from programming languages, from programming, a string is just a finite sequence of characters. So in mathematics, a set of strings is going to be called a language, and it's going to basically be how we represent a computational task. Okay, so a computational task in which we're given an input, we expect some output. Often we're going to be given an input that's a string, and the output we expect is just true or false, is Boolean. And in that setting, a language sort of captures, it's basically going to represent all the strings you're supposed to accept. So language is a set of strings. That's kind of, you can think of it as the strings that you're supposed to accept in some computational task. So the languages, any string not in the languages are string you're supposed to reject. So you're supposed to output false, basically, on the strings not in the language. Okay, so having said that, so let's just quickly go to the formal definition of a language, which is also in the notes. So to start with that, we start with talking about sets. Hopefully you're all somewhat familiar with sets. So sets in mathematics are just kind of containers that contain an unordered collection of elements. So like a set can be, here's a set, 1, 2, 3. This is a set. Another set can be just 1 and 5. You've probably seen sets before. We can do various separations on sets. So we can take the union of sets. So this U denotes the union. And if we take the union of two sets, we just pool together the elements that are in both. We kind of pour them into the same bag, and we get the set 1, 2, 3, 5. And note that 1 was in both sets. So you would think that we get 2 copies of the element 1, but in mathematics, when we talk about a set, we don't allow duplicate elements. So a set can only contain 1 of each element. So here, the 2 copies of 1 just become a single copy of 1, and we get a set of 1, 2, 3, and 5. So this is the union of these 2 sets. We can also take the intersection of 2 sets, which gives us the elements that are in both. So if we take 1, 2, 3, and we take intersection, this symbol, the upside down U, denotes the intersection with 1 and 5. Then we get the set 1. It contains 1 element. Okay, so you've probably seen this before. A union is sort of like a logical OR. We take the elements that are in set A or set B. An intersection is sort of like a logical AND. We can do other things with sets. We can look at the size of a set. So we can look at the size of the set 1, 5. This is kind of denoted with absolute values, and that's going to be 2. Okay. We're going to encounter the empty set a lot. This symbol is going to denote the empty set. So you can also denote it with a set with nothing in it, just brackets and nothing inside. Okay, so this is the empty set. The size of the empty set is 0. It contains no elements. Okay. You should be a little bit careful with the empty set, and that, the confusing things can happen with it. We can put it inside of another set. So what is this? This is actually, it's actually this thing. It's a set containing the empty set. Okay, so the size of that object, the size of this thing here is actually 1. There's 1 element in that set. The empty set is in that set. It's a set containing the empty set, so the set contains 1 element. Okay. All right, fine. Of course, the empty set contains no elements, so the intersection of the empty set with anything else is equal to the empty set. Just more generally, the union of the empty set with any set A is equal to A. Okay, so this is pretty straightforward. Sets in mathematics can be infinite, so we can take the set A to be the set of all 1, 2, 3, 4, and just both put dot, dot, dot to mean all the natural numbers. Okay, so sets are allowed to be infinite. This is a valid set. And we can still take unions and intersections of these infinite sets. So we can talk about the cardinality of an infinite set. This is the size of an infinite set. So of course this will be infinity. But as it turns out, and as we show in the notes, it's not enough to say that the size is infinity, because there's sort of different sizes of infinity. There's different cardinalities of infinite sets. And what do we mean by that? So there's a bit of a tricky notion. How do we talk about the size of an infinite set? Well, the size of a set should not depend on the names of the elements in the set, on what the elements are in the set. So, if we have, for example, if we have another set B here, and this set B is the set 2, 4, 6, 8 of all the even numbers. So in a sense, B looks smaller than A, and it is a subset of A, a strict subset of A. It has some of the elements in A, but not all the elements in A. Okay, but you can see that I lined up B below A, and you could kind of see that this first element of A, imagine I just renamed it. Instead of calling it 1, I call it 2. That's just a naming convention, right? I can change languages, and maybe in my different language, the symbol 2 means 1, right? So you can just think of this as sort of a renaming of all the elements. I matched them 1 to 1, gave them each a new name. And so it should be clear from the fact that I can match all the elements in B uniquely to elements in A. I have a 1-to-1 matching that's made possible by the fact that these are infinite sets, because they go to infinity. I'll never run out of things to match. So, because of this, you can think of B as just a renaming of all the elements in A. This is a kind of sounds like the size of B should be the same as the size of A. So in one sense, it sounds like the size of B should be smaller than the size of A, because it's a strict subset. It's strictly smaller than A. But in another sense, look, we lined up the elements. Clearly, it's the same number if they can be matched perfectly, the set B and the set A. If it's just a renaming, then clearly it feels like it should be the same number of elements. So in mathematics, we do call these sets the same cardinality. We say they're the same size. Even though B is a strict subset of A, B is still the same cardinality as A. It's still the same size as A. And that's made possible by the fact that they're infinite. Okay, so when you get to infinite sets, doubling the number of elements still stays you at the same size. Okay, so or even adding an element or subtracting an element, those operations maintain the same size of the set if the set is infinite. So they don't change the size of the set because of this renaming trick, because we can sort of match them 1-to-1. So we can define sets to be the same size if they can be matched in a 1-to-1 correspondence in this way. And then you can ask, okay, are there infinite sets that cannot be matched 1-to-1 with each other? Are all infinite sets the same size according to this definition? And it turns out the answer is no. So these two particular infinite sets are the same size, A and B here. The natural numbers and the even numbers, they're the same cardinality. Okay, but we can get bigger sets that are not the same cardinality. And the kind of standard example or the standard construction of a set that's not of the same size as A is the power set of A. So the power set of A, so we call this P of A. The power set of A is the set of all subsets of A. Okay. So I'm going a little bit quickly because I assume you know what a subset is, that you've seen subsets before. It's all in the notes if you haven't. A subset of A is a set that contains some of the same elements as A. So this power set of A contains all of the subsets of A. Okay, so if A were finite, so well, let's just do an example with a finite set. So the power set of the set 1, 2 is the set that contains all the subsets of that set. What are all the subsets? There's this is a subset. This is containing only 1, this is containing only 2. The set itself is a subset. Okay, we don't require it to be a strict subset. So the set itself is a subset. And actually there's another one. The empty set is a subset. Okay, the empty set contains only elements that are in the original set because it contains no elements. So that's kind of a trivial statement. Okay, so the power set of a set of size 2 is a set of size 4. We have 4 elements here. And in general, the power set of a set of size n is 2 to the n. Okay, and that's kind of an argument in the notes that each element is either, when you're defining a subset, you can either include or not include each element. So if there are n elements, there's sort of n different choices of yes, no. And the number of ways to make n such choices is 2 times 2 times 2 times 2, n times. So it's 2 to the n. So there's 2 to the n different possible subsets you can specify of n elements. Okay, so this is for a finite set. So this is the power set of a finite set. We can also take the power set of an infinite set, and it turns out you'll always get a larger set. Okay, and that is shown in the notes. Let's briefly sketch the argument. Why not? It's kind of a fun argument. The argument kind of goes by contradiction. It's suppose that the power set, suppose you have a one-to-one matching between the power set of A, and suppose you can match all the elements in it. You want to kind of match all of them to the set A, right? So you want to list all the elements here and list all the elements here and kind of do a one-to-one matching and not miss any elements and not count. Not miss any elements on the left or use any elements on the right twice, just a one-to-one matching. Okay, so suppose you can do this. Clearly we cannot do it if A were finite, but here A is infinite. So, how can we rule out this possibility? And so the answer is, okay, so the trick that Cantor came up with was to say, okay, so suppose we could do this, so each thing on the left is a subset of A, right? On the left, we have all the subsets of A. On the right, we have the elements of A that we're listing out. Okay, so for each subset of A, so suppose B here is something on the left, it's a subset of A. It's gonna get matched to some element X. Okay, so we have here, X is in A, it's an element of A, and B is a subset of A. Okay, and so we have these matchings, and we can ask, is it true that X is in B? Okay, for where X is the element that's matched to B by our matching. So we suppose that somebody gave us a matching, and then we can ask for each subset whether the element it's matched to is in the subset or not, right? So we can ask, is X in B? Yes or no? Okay, and then we could say, okay, if yes, that's cool. Okay, so all right. If no, let's call that bad, or let's call that lame. Let's see. So if no, we will call it lame. Okay, so we have these lame subsets. They're not cool. All right. So okay, so a set of is cool if the element that's matches to under this matching, this one-to-one matching, is in the set. Okay. So some sets are cool, some are lame. Okay, we don't know. Somebody just gave us this one-to-one matching. All right. So now we can say, all right. So well, also we can call each element either cool or lame based on whether it's in the subset it's matched to, right? The same definition. So if yes, then we have a cool here. So X is cool too. So X is lame if X is not in the set it matches to. Okay, so now we can talk about all the lame elements, right? So we can say, okay, so let's take the set of all X in A such that X is lame. All right, that depends on this one-to-one matching we were given, right? Somebody gave us a one-to-one matching. We want to show that's impossible. We want to give a contradiction. So we will define the set that's depends on the one-to-one matching, because our definition of lame depended on the one-to-one matching. But we can define this set, right? Let's call this set C. Okay, so C is the set of all elements that are lame, right? They're not in the element they match to. Okay, so now we can see, all right, so C is a subset of A, right? C is a subset of A. So it's somewhere on the left. Somewhere on the left we have C, and C is matching to something, right? So C is matching to Y, and we know that Y is some element in A, right? So now we can ask, is Y in C? Whoops. Is Y in C? Or in other words, is C cool? Right. So C contains all the lame elements. So in some sense, it's really lame. But you know, our formal definition was that a set is cool if it contains the element it matches to. So does C contain the element it matches to? Okay. So does C contain the element it matches to? So if C, how was C defined? C is defined as containing all the elements that are not in the set they match to. Okay, so kind of think of these two possibilities. If Y is in C, okay, so if C contains the elements it matches to, then Y would be cool, right? But then by definition of C cannot contain Y, because C only contains the lame elements. Okay, so clearly we must have that Y is not in C, right? But if Y is not in C, then Y would be lame by definition of lameness, because Y is matched to C, right? So if Y is not in C, then Y is by definition lame. But then by the definition of C, Y C would contain Y, right? But so we get a contradiction either way. We get this kind of paradox, this self-eating paradox. This definition of C is kind of not stable. The definition of C secretly talked about itself, because it talked about kind of for every element it talked about the set it was matched to, but some element is matched to C, right? So the set C looks well defined, but secretly it's kind of talking about itself, and it's contradicting itself, all right? But it's only talking about itself because somebody gave us this magical matching, this bijection, I guess, between the power set of A and A. And so anyway, it turns out there's no way to avoid the paradox except to say that there could not have been such a matching in the first place. There's such a one-to-one matching. So actually, this turns out to be a proof that there is no one-to-one matching. If there was a one-to-one matching, you know, then you know, this set C wouldn't make sense. So it's like I think there's this example of imagine trying to create the Wikipedia article that links to all Wikipedia articles that don't link to themselves, right? The Wikipedia article will just contain links to all the wiki articles that don't link to themselves. Okay, so that's fine so far as it goes, except does this article link to itself or not, right? And you can see that either way, it fails to achieve this property of linking to all articles that don't link to themselves, right? So you know, you kind of get a contradiction. There can't be a Wikipedia article that links to all articles that don't link to themselves, because either it links to itself or it doesn't. So it will be wrong about itself. Okay. So for the same reason, well, I mean, Wikipedia articles don't try to be to contain all possible sets of links, right? So if you did try to create all possible sets of links, then you're going to have a problem in kind of a similar way here, that you would not be able to let's see. You would not be able to uniquely match the links to the sets of links. There's strictly more sets of links than there are links. You can't give a one-to-one matching between a set and its power set. Okay, so this proof is a bit confusing. I think the coverage in the notes is a little bit more clear. Post on Piazza if you have further questions about it. So for now, let's move on. Okay, so we just said, okay, so not all infinite sets are of the same cardinality. The power set of a set is always a larger cardinality, has more elements, even when you're talking about infinite sets. So for our purposes, we will only kind of deal with two different types of infinity, really. We will say that let us say A is countable if we say that A is countable if it's either finite or it's infinite, but has a one-to-one matching to the set of natural numbers. Let's start with 0. So I said A is countable if it's either finite or it has the same size as the natural numbers, and the natural numbers turn out to be the smallest infinity, basically. So it's countable if it's infinite, but not that infinite. It's the smallest infinite or smaller, right? So it's countable if it's, either finite or, not that infinite, infinite, but only countably, so only the same size of the natural numbers. And A is uncountable otherwise. So uncountable sets are like super large. They're so large that you can't even list all their elements in order. The real numbers, the set R of real numbers, is uncountable. Okay, we can't even have a one-to-one matching between the real numbers and the natural numbers. Okay, so that's all I wanted to say for now about that. Let's briefly talk about languages. Hold on. Okay, so let's briefly talk about languages and strings. Okay, so we know about sets now. Let me just briefly cover strings. So strings are, well, to define a string, we first need an alphabet. An alphabet is going to be a set that's going to be non-empty but finite. So an alphabet is a set. It's going to usually be 0, 1. Sometimes it's going to be, a bit bigger, like A, B, C. But in any case, it must be finite and it must be non-empty. So that's an alphabet. A string over that alphabet is a finite sequence. So a string is a finite sequence of characters from the alphabet. Okay, so this is a string. This is a string. Oh, that's over 0, 1. So these are strings over 0, 1. Yeah, so this is a string. All right. These are all strings. Here's this one. This is not a string. This with infinitely many zeros. So infinite sequences are not strings. Okay. Okay, so that's not allowed. A string must be finite. We will also have the empty string. We'll denote it by a little epsilon, this epsilon here. So that's the empty string. It's kind of, think about it as kind of begin quote, end quote in your favorite programming language, I guess. It's just a string of length 0. So for a string, we can talk about its length just like we did for a set. So the length of 0, 1 is 2, right? And the length of the empty string is 0. And so the length of the string is always going to be finite, no infinite strings, right? That's not a string. All right, good. Unlike for sets are allowed to be infinite, strings are not allowed to be infinite. That's just a terminology thing. Okay, so good. For two strings, we can take the concatenation, right? So if x is a string and y is a string, then we can take xy. So let's say x is 0, 1, and let's say y is 1. Then xy would be 0, 1, 1. So here we put them next to each other. It kind of looks like a product, right? If there were numbers, this would kind of be a product. But since they're strings, it's going to be the concatenation, the gluing together of the strings by writing one sequence and then writing the other. Okay, so this is the concatenation of two strings, and the concatenation of any string with the empty string is the same string. Right. So because we're gluing 0 additional characters, so that we didn't change the string. Good. So a set of strings is called a language. Okay, so this is kind of going to be a key object in this class. So a language is a set of strings. Okay, so now technically we only define strings with respect to an alphabet. So we need to be a little bit careful. So we should say a language, we should define it over an alphabet. So we kind of want to define it with respect to an alphabet. Sometimes the alphabet is kind of implicit, but yeah, a language over an alphabet sigma is a set of strings over sigma. Okay, so that's a language. A language is a set of strings. Okay, so note that languages are allowed to be infinite, even though strings are finite. Okay, so for example, so we usually use capital letters for languages. Okay, here's a language. This is a language because it's a set of strings, right? So this is a language of size 4. We have 4 strings. One of them is the empty string, but it's still a string, so it still counts as one of the elements when we count the cardinality of A. Okay, here's another language. All right, this one, let me call it B. Okay, so here the set of B is 0. Okay, here's another language. This is the set containing the empty string. So the set of this, the size of this language, cardinality of this language is 1. So note that the empty set and the set containing the empty string are not the same set, right? They're two different things. They're two different languages. Okay. All right, fine. Here's a fourth language. So these are all over. Let's say we pick our alphabet to be 0, 1 for now. Okay. So here's another language over 0, 1. 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. Okay. You can say, hold on, can this really go to infinity? So let's go to infinity. And can this really go to infinity? We said we're not allowed infinite strings. And the answer is it is because each string is going to be finite. So each string in D is going to be finite. There's just going to be infinitely many of them, one for each natural number, right? So D will contain a string of length 100 and a string of length 1,000 and a string of length 1,000,000. And for every number, it will constrain a string of that length, but no string of infinite length. Okay, there will not be any one string you can point to and say that is infinity. No, that's not allowed. So for any natural number, all natural numbers are just finite numbers. For any natural number, D will contain a string of that length. right? But there's no last natural number. There's no natural number called infinity. And so D will not contain a string of length infinity, okay? And that makes D a valid set of strings and therefore a valid language. And the cardinality of D is it's infinite. So this is, let's just write infinite, but countable. Countable because we can put it in one-to-one correspondence with the natural numbers like this. So here I'm putting it in one-to-one correspondence with the natural numbers. Okay, that's pretty easy to do. Okay, so it's infinite but countable. Okay, so that's a valid language. Languages are allowed to be infinite, even though they only contain finite things. Okay, because there's infinitely many finite things. Okay, great. So those are languages. Let's just talk briefly about a couple operations we can do with languages. So let's say that A and B are languages. Languages over an alphabet sigma. Okay, so then we can take A union B, right? So A union B is also a language over sigma, because it also contains, it's also a set of finite strings over sigma. If both A and B are, then this is still a finite set of strings, sorry, a set of finite strings rather, over sigma. Yes. So the union is a language, the intersection is a language. Okay, we can also define the concatenation. Okay, so this is going to be defined as the set of all string concatenations xy, such that x came from A and y came from B. Okay, and that's also a language. That's also a language over sigma. Okay, so let's just do an example of language concatenation. We can say, let's say A was 0, 0, 1, 0, and let's say B was epsilon and 1. Okay, then AB would contain the concatenation of this string with this one, which is 0, 0, and it would also contain the concatenation of this string with this one, which is 0, 0, 1. It will also contain the concatenation of this string with this one, which is 1, 0, and also this one with this one, which is 1, 0, 1. So we took all ways of combining, of concatenating together some string from A with some string from B. Okay, one from A, one from B, the one from A on the left, the one from B on the right. And all ways of doing this form the set AD, and that's still a language. Okay, so we can concatenate languages together, and that gives us a new language. You know, the sizes, it can be as much as the product of the sizes of A and B. Sometimes it's less, because sometimes you get overlaps where you kind of you get redundancy. Some strings can be formed in multiple ways by concatenating together strings from A and strings from B. Okay, here's another operation. So another operation we can do is called the clean star. So if A is a language, A star is going to be whoops, sorry. It's going to be this. It's going to be the union of the set containing the empty string and the set A itself, and the concatenation of A with A, and the concatenation of A with A with A, and so on. So it's going to be this union of infinitely many such languages. Each one of them is going to be a language though, right? So at each finite point, we get a concatenation of n copies of A together. That's going to be still a language because we just concatenating n languages, each of which contains finite strings. So you only get a new language out of it. And we do this for each natural number n. So we never concatenate an A with itself infinitely many types. That's not allowed. So we cannot concatenate. We cannot do. So here's the so not allowed. So here's not allowed. Doing a to infinity. So this is bad. This is not allowed. Okay. Do not concatenate languages with themselves infinitely many times. That's not okay. All right, but we can take infinite unions, and here we are combining together infinitely many languages, each of which contain only finite strings. So the union only contains strings that were in one of the original languages, and each of those is finite. So even the union of infinitely many of these still only contains finite strings. Okay. All right, so this is the clean star. This is the definition of a star. We will usually just write star. So we should do a couple examples. Let's say that A was the set containing 0. Then A star, what would A star be? A star would actually be, well, it would contain the empty string because of this one. And then it would contain 0 because we are unioning together the set A itself. And then it will contain 0, 0 because we take this union of A, concatenate A. And then 0, 0, 0, 0, 0, 0, 0, and so on. So it's going to be the set that contains all strings that contain only zeros of any length, of any finite length. Okay, so it's an infinite set. Right. Let's try another example. So let's say B is the empty set. Okay, then B star, by the way we defined it, is just going to be the set containing the empty string. So it's actually not the same. Okay, fine. Let's try another one. So then C star. C star is going to look like, well, it's going to have the empty string. It's going to have 0 and 1, 1. Then it's going to have, you know, anything that you can make by gluing 0 and 1, 1 blocks together. So it's going to contain things like 0, 0 and 1, 1, 1, 1, and also 0, 0, 1, 1, 0, 1, 1, 0, 0, 0. I'm not writing them in order or anything, but it will contain all strings you can form by gluing together any number of zeros and any number of 1, 1 blocks in any order you want. Okay. So one thing to note is that sigma star is actually going to be the set of all strings over sigma. So sigma star is going to be all the things you can form by gluing together elements of sigma with each other. But the elements of sigma are the characters out of which we get to form strings over sigma. So the elements of sigma star are all the finite strings, so all the strings over sigma. Okay, so basically, if A is a language, whoops. If A is a language over sigma, then A is a subset of sigma star. Because sigma star contains all the finite strings. So if A is a language, then it contains some set of finite strings. A is some set of finite strings. So it must be a subset of sigma star. So sigma star is the largest language over sigma. Okay. And in the notes, we argue that sigma star, it turns out, sigma star is actually countable. So although it's infinite, because sigma is a finite non-empty set, so sigma star will be infinite, but it will be countably infinite. So countable infinite. And that's the largest language. It's a superset of every language over sigma. So every language is countable. So all languages are countable. Okay. Even though all languages are countable, they're each individually countable. The number of languages over sigma is uncountable. Okay, right? Because so what is the set of all languages? The set of all languages is a set of all subsets of sigma star, right? So languages over sigma are subsets of sigma star. So they are elements. They're elements of the power set of sigma star. Right? This is the set of all subsets of sigma star. Okay. We know that the power set of sigma star is strictly bigger than the size of the power set is strictly bigger than the size of the original set, which is countably infinite. Okay, so that this thing, this power set of sigma star is uncountable. Okay, so the number of languages over sigma is uncountable, but each language is a countable set. Okay, so each language is a countable set, sometimes infinite, of finite strings. Okay, so each string is finite. Each language is maybe finite, maybe infinite, but at most countably infinite. So it's always countable. But the number of languages, so the set of all languages, is uncountable. Okay, and that's for a fixed alphabet. For any fixed alphabet, all of this holds. Okay, fine. All right, so now let's briefly talk about the regular operations. The regular operations. So we talked about several operations you can do in languages, but there are three that are considered special, and we'll call them the regular operations. So union. So A union B is a regular operation. Concat. Concatenation. This is AB. We've talked about that. That's a regular operation. And then star. This is the clean star. Okay. So these are the three regular operations. So a language is called regular if we can build it from simple blocks. Using the regular operations. Whoops. Okay, so in particular, a language is regular if we can, if either, let's write the definition like this. So the empty set is regular. Empty set is a set of strings, so it's a language. It's a regular language. The set containing the empty string is regular. Okay. The set containing a character C is regular. Let me just write is reg for each C in sigma. So for each character in sigma, then the set containing that character is regular. Okay, and then if A, B are reg, then A union B is reg. If AB are reg, then AB reg. If A reg, then A star reg. Okay, so reg here stands for regular. So these are this is basically the definition. The definition is all these very simple languages, the simplest possible languages that you can think of, the building blocks, those are all regular. So the empty set, the set containing the empty string, and the set containing any one character string, all those are regular. And then anything you can form out of them using the regular operations, those are all regular. Okay, so you can union them together or take star of them or concatenate them together, and anything you get as a result is regular. Okay, so you know, for example, sigma star is regular. Why? Why is sigma star regular? Well, because sigma is equal to, you know, the set containing C1 union the set containing C2 union up to the set containing CD if sigma is consists of the characters C1, C2 up to CD. Okay, so then we can write sigma as a union of these simple pieces, and these simple pieces we said are each regular, and union is a regular operation. We're allowed to take unions, and that keeps it regular. So sigma is regular, and then star is a regular operation. So we take our language we showed as regular, and we took the star of it, and that's regular. So sigma star is regular. So the set of all strings is regular. Okay, but not every language is regular. So the set of all strings, the largest language, is regular. Okay, and also the empty set is regular. The largest and the smallest languages are regular, but many of the ones in between are not. So regularity doesn't measure size. It kind of measures simplicity. So both the set containing all strings is pretty simple to describe, right? And the set containing no strings is pretty simple. But in between, you can have complicated sets, and some of them will not be regular. Okay, so not all languages are regular. In other words, some subsets of sigma star are not regular, even though sigma star is regular. So sigma star is regular, right? Sigma star is regular, but some subsets are not. Okay, that's allowed. That's fine. So regularity only it doesn't correspond to size. It corresponds kind of to simplicity. So some sets are subsets of sigma star, and they can be smaller, but they're more complicated. Okay, and it turns out that finite languages are regular. Okay, and we discussed that in the notes. So now let's talk briefly about regular expressions. Reg x's. So regular expressions they're shorthand for how this recipe of how to show a language is regular. So we know to show a language is regular, we take unions, concatenations, and stars, starting from the basic building blocks of the empty set, the set containing the empty string, and the single characters. Okay, so we start from these basic building blocks, and then we show a language is regular by constructing the language with the regular operation. So a regular expression is exactly that, is the recipe, basically. for how to construct a language. So just basically, it's a bit of a shorthand. So instead of writing something like 0, union 1 star. Sorry. Let me just hold on. So instead of writing 0 union 1 star like this, we write 0 union 1 star. Okay, so we removed a bunch of brackets. Okay, in a regular expression. So this is a regular expression. So this is regx, as we will write it in this class. So a regular expression is actually just a string. Okay, so regx's are actually strings, but not over the original alphabet, over an expanded alphabet. So they're strings over this alphabet, sigma union, the character union, and then the character star, the character epsilon, maybe that's it. Okay. Character epsilon. The notes have a more complete description. So basically, it's a string that defines a recipe for how to create a language over sigma. Okay, so the recipe so this recipe, 0 union 1 star, means, take the set 0. So the symbol 0 is going to correspond to the set containing the character 0. And then union it with the set containing 1 star, where we took a clean star. Okay, which is going to be 0 1 1 1 1 1 1 1 1 1 1. It's going to have this single 0 together with all these ones of any length, any number of ones. Okay, so we will use this notation. L of R will be the language of regx R. Okay, so if R is a regular expression, L of R is going to be the language of R. Okay, so we can talk about L of 0 union 1 star, and and that's going to be the set we wrote before. Oh, I missed epsilon. 0 epsilon 1 1 1. Okay, so that's the language of this regular expression. Okay, so this regular expression, think of it as a string. Okay, a string that defines a recipe, and kind of L kind of compiles the string into the language it represents. Okay, so think of this as just kind of code, right? And L takes that code and builds the language out of it. Okay, so the regular expression is the code, is the string, and L operation builds the language out of it. Okay. So basically a language A is regular if A equals L of R for some regx R. Okay, so it's a language is regular if you can have a regular expression that generates it exactly. Okay, so and we want equality here. We don't want just A to be a subset of L of R or something. We want R to generate the strings in A and only the strings in A. Okay, we care that we don't over-generate more strings than A contains. Okay, all right, so that's regular expressions. The notes have a few more examples and details. Okay, so but it turns out there's another definition of a computational model, a machine. that turns out to correspond to the regular languages. So let's talk about this. DFAs. DFAs are deterministic finite automata. So DFAs are these machines that have these states, like, so they have these states. We'll call them Q0, Q1, Q2 in this case, and then you're given kind of transitions between them that are labeled by alphabet symbols. Okay, so I'm just gonna kind of label them and see what happens. So you can have loops. Okay, so here's a simple example of a DFA. Let's okay, here's a simple example of a DFA. There's a couple of things going on in this diagram. So first of all, we have states. The states are these circles. Okay, so the circles are states. Some states have double circle. Those are accept states. Okay, double circle means the state is accepting. We'll see what this means in a second. And there's arrows between the states, and the arrow tell you how to move when you see a symbol. So if you're at state Q0 and you see the symbol 0, you move to state Q1. Whereas if you're here at Q0 and you see 1, somebody gives you a 1, then you go over here to Q2. Okay, so this diagram just tells you how you change when you see symbols. So for example, if you're at Q1 and you see a 1, you stay in Q1. You just move back to Q1. If you see a 0, you move to Q2. All right. And this arrow from nowhere, it just goes to indicate the starting state. So the arrow from nowhere is going to point to Q0, and it's going to tell us where we start. Okay, so here we start at Q0. Okay, and this machine can take a string and either accept it or not. We say it accepts the string if once it reads the string, at the end of reading the strings, it reaches the accept state. So let's just give an example. So let's say this machine reads the string 110. Okay, so this is input. So this over here in this rectangle here is going to be a machine. It's called a DFA. So okay, so it's DFA. This is the machine, and this is the input to the machine. Okay, so if we kind of feed that into the box, what will the box do? Okay, so the box, this DFA, it will read the string 1 bit at a time, 1 character at a time. So it first reads this 1 over here. First it reads this 1. Okay, now the machine starts at Q0 and it reads a 1. Okay, so it starts at Q0. At the beginning, the state of the machine is at Q0. Then it reads a 1, which means it transitions to Q2. Okay, it reads another 1. Okay, which makes it transition using this arc here. It transitions back to Q0. Okay, and then it sees a 0. Okay, and it's at Q0, so it goes to Q1. Okay, then the string ends. So the final state is Q1. Okay, the final state is Q1, and Q1 is not circled twice. It's circled only once. So it's not an accept state. So the DFA rejects. So if you feed in 110, the output will be reject. Okay, this is how a DFA works. Okay. It's kind of useful to play around with these things. So the DFAs are kind of these, think of these really, really simple machines. They just only have a couple of different states they can be on. They can be kind of one of these, sometimes children's stories feels like they're secretly DFA. Like it kind of has a mode where it has one light on or another light on, or maybe a sound is happening, and as you press buttons, it switches between the modes. DFA is just something simple like this, but we label some states of accept states. Okay, and if you end at an accept state, if you finish reading the string at an accept state, you accept. Otherwise, you reject. In this case, note that we passed through to Q2 in the middle. We reached an accept state in the middle, but we did not accept because we didn't finish reading the string. Okay, so only when you finish reading the string do check whether your state is accept state or reject state. Okay, and in this case, it was not an accept state, so it rejected. Okay, now DFA have the DFAs have these formal. They have these formal definitions, which is like this tuple, right, of a set of states Q, right, and let's see if I remember all the ingredients. And then alphabet sigma, this is the alphabet of characters it uses. And then there's this transition function. And then there's a start state and a set of accept states. So read the notes for the formal definition. I don't want to go through it in this video, but there is a mathematical definition of what exactly that specifies all the ingredients to draw a state diagram. Okay, so all the ingredients is you need names for the states just so you can talk about them. You need to know what alphabet, what you're working on in the first place so that you know how to label your arrows. Then you need a function that basically takes, the function basically takes one state and one character, and it gives you another state, you know, so this function has signature Q times sigma to Q. It takes these pairs of state and symbol and gives you a different state to go to. So that tells you, basically specifies all the arrows and their labels for where you go when you see what. Then there's the start state. This gives you the kind of arrow from nowhere. And then there's the set of accept states. So F here is going to be a subset of Q. So Q0 is going to be an element of Q. Q0 is going to be an element of Q, and F is going to be a subset of Q. And the subset specifies all the accept states, all the states circled twice. So you're allowed to have more than one of them. So you're allowed to have a DFA that where even every you know, you can have this. These are zeros. These are doubly circled states. That's a valid DFA. So I mean, over the alphabet, over this alphabet, sigma equals 0. So you're allowed to have every state be an accept state if you want, or multiple states to be accept states. Okay, so F here specifies which states are accept states. Okay, so that's DFA. So this is one kind of notion of a machine. For a DFA, we can talk, so let's say we call this thing M, okay? We can talk about the language of M. So the language of M is the set of all strings. So here I'm gonna denote X in sigma star to make sure that X is a string, right? Remember, sigma star is a set of all strings over sigma, such that, you know, M of X accepts. Okay, so M of X, the behavior of M of X is defined formally in the notes, but informally it's just kind of what happens when you run the machine M on the string X, right? We did this before. We ran one example of a DFA, one example of a machine. We ran it on the string, what was it, 110? Or 001 or something, whatever. So we just did an example, and we got a reject state at the end. So here, L of M is going to be all the strings where, when you run the machine like that, starting from the start states, from the initial state, you will get to a state in F. You will get to an accept state. Okay. So this is a function of the DFA M. Okay, for any given M, you can define a language, which is the language of strings it accepts. Okay, the L of M contains a string if and only if M accepts that string. Okay, and that's for a DFA. And similarly, the notes also define another very similar model called an NFA. So NFAs are non-deterministic finite automata. So DFAs are deterministic ones and NFAs are non-deterministic ones. The non-deterministic ones just try to make your life easier when you construct these things. And they give you more power. So they kind of say, all right, first of all, we'll allow multiple transitions. So if we have kind of a start state, Q0 or whatever, will allow multiple transitions labeled by the same thing. Okay, so you can go to either Q1 or you can go to Q2. Okay, when you see a 0. We will also allow you to not draw transitions. So here, there's no transition coming out of Q0 when you see a 1. If you see a 1 coming out of Q1, you loop. If you see, or you can go to Q2, let's say. So you can, it's ambiguity, you can do either. And we'll also allow you to label arcs with epsilon. Okay, if you label arc with epsilon, it means you can take it for free without even reading anything. Okay, so then let's say if you see a 0, you can go back there. And you know, as usual, you can you double circle to denote accept state. So the differences are you can have multiple transitions with same label. You know, from same state. And you can also have epsilon transitions, which are transitions you can take for free. And you can have missing transitions. So these are things you were not allowed to have in DFAs. So what does an NFA do when it reads a string? Well, it actually can do many things. Okay, so let's say we read the string. Let's say we read the string 0, 0. Okay, so when we read the string 0, 0, when we see the first 0, so we start at Q0, right? So we start at Q0. When we see the first 0, we actually have two options of where to go. We can go to Q1, okay, or we can go to Q2, okay, and we can go to either one when we read the first 0, right? Because we have two transitions here that are labeled by 0. Now from Q1, if we see another 0, there's nowhere to go. So we just kind of reach a contradiction. Let's just put a big X here. Something bad happened. We didn't find a place to go. Okay, if we didn't find a place to go, this path can't be taken. It's basically a reject path, but we'll talk about that in a second. Okay, so from Q2, before we read the next 0, there's actually an epsilon transition. So we're actually optional. We can either stay at Q2 before. So here, when we read a 0, we can go to either Q1 or Q2. But here, from Q2, we can either stay at Q2 and read nothing, or we can read nothing and go to Q1 because of this epsilon transition over there. The epsilon transition can be taken without reading anything. Okay. Now, when we read the next 0, if we were at Q1, there's nowhere to go. Okay. So, but if we are at Q2, we can read a 0 and return to Q0. Okay. Now Q0 is not an accept state, so we reject. Okay. So the rule for NFA is, so here we kind of did an example, but the general rule for NFA is that we accept a string if there's some path you can take that reaches an accept state at the end of reading all the strings. So you must read all the string and you must reach an accept state according to some path. But you can take any path you want that's legal, and you can take epsilon transitions for free. Okay, so you're allowed to take, so you see, if you see a Q0 here, and you have an epsilon transition, or a 0 here, and you see a Q1, and there's a 0 here, and Q2. So let's say this is your Q2, Q3. Let's say this is your NFA, and you're reading the character 0. If you're reading the symbol 0, you start as Q0. You could go here to Q3, but Q3 is not an accept state. Okay, or you could first, before reading 0, take the epsilon jump to Q1, then you can read the 0, get to Q2, and then Q2 is an accept state. Okay, so here you accept. So this NFA actually accepts 0. What about 0, 0? So this is accepted by this NFA. What about the string 0, 0? Well, here, after reading 0, we know that you could have ended up at Q0, or you could have ended up at Q2, sorry, at Q3, or you can have ended up at Q2, right? So you could be here, or you could be here at Q2. But neither of them have an arc for the second 0. So there's no way to take the second 0 and go anywhere, actually, let alone in accept states. So this is reject. Okay, so if you have nowhere to go, you sort of must reject that path. Whenever you have a path and you have nowhere to go in an NFA, it's an automatic reject. Okay. So, all right. So this is kind of an NFA. It's a bit more complicated than a DFA. However, it's often kind of easier to construct for languages. It's often easier to construct NFAs than DFAs. So they're kind of a useful definition. Now, in the notes, we also have a formal definition of NFAs. They're also kind of these tuples, Q and sigma, and they have a different definition of a transition function. They still have a start state, though, and they still have a set of accept states. So it's kind of a similar thing, but this delta is now, it takes in, you know, it takes in a state and a symbol, and it kind of gives you a set of states you can go to, and it can also sorry, I kind of messed up this definition. It's also allowed. There are also epsilon transitions, so you have something like this. I think it's something like this. The notes have the formal version. So the signature of delta of the transition function is different in order to allow for these the more general NFAs. Okay, but that's the basic gist of them. So we will do some example of them in the notes to hopefully clarify. Okay, and so if you have, if n is an NFA, then we can again write L of n to denote the set of all x such that, so let's say x in, so these are string, x in sigma star to show that x is a string, the set of all x such that n of x accepts. Accepts means has an accepting path. Okay, so this is L of n. This is the language of the NFAN. The language of NFAN is the set of all strings for which that NFA can reach an accepting path. So those are the strings the NFA accepts. So it's sort of a similar definition to the language of the DFA, except there's many paths here, and we just care about the existence of even one accepting path that would make you accept the string. Okay, so this is the language of an NFA, and then the kind of claim, or the main claim of this part of the course, the kind of interesting claim that we see in the fourth lecture, is the following: that you know, A is regular. Oops. So let's write it like this: A has regex if and only if A has DFA, which is if and only if A has NFA. Okay, so the power of all the three models is the same. So in other words, you know, there exists a regex R such that L of R equals A. That statement is equivalent to the statement exists a DFA M such that L of M equals A. And that's equivalent to saying there exists an NFA N such that L of N equals A. So all those three ways of constructing languages, one by building a DFA that accepts, recognizes the language, I guess it's called, or building an NFA that recognizes language, or building a regular expression that generates a language. Those three things give rise to the same class of languages, the same regular languages. Okay, so those languages are called regular if any of these definitions are satisfied, and these definitions are all equivalent. And so let's just kind of give a 2-minute sketch of the proof. Okay, so the 2-minute version is that, well, the notes have the full version, of course, but the 2-minute version is, of course, that, you know, if A has DFA, it has NFA, you know, because NFAs are more general. They allow strictly more things to be done in your machine. It's strictly more types of transitions. You don't have to use any of these epsilon transition nonsense if you don't want to. You can just make a DFA, even though you're strictly speaking defining an NFA. So of course, if A has a DFA, it has an NFA. To go backwards, now if A has an NFA, if A has an NFA, then if A has an NFA, then we want to build a DFA. And to build the DFA, we have where we have a state of the DFA for each set of states of the NFA. Okay, that's because one way to think of what an NFA is doing is that at any point in time, the NFA has a set of states where it might be in right now, right? So when you think of an NFA and what it's doing, when it reads a character, it might go to multiple places, but really there's only one set of places where it can be. So if you take the set of all states where it could currently be right now, that's a well-defined set of states. So we will have a DFA that has one state for each set of states of the NFA. And the DFA will transition from one set of states to another set of states exactly when the NFA is allowed to move from that set of possibilities to exactly that set of possibilities. Okay, so we can define, so the DFA will be exponentially bigger, right? So if the NFA had n states, if the NFA has n states, the DFA is just going to have 2 of the n states, one for each set of states of the NFA. So we're going to have a lot more states and a lot more transitions, but each transition is going to be deterministic now because each time the NFA reads a new symbol, it can go from one set of possibilities to a new set of possibilities of where it is next. But these are just 2 fixed sets. So we will draw an arc between these 2 sets in the DFA, right? So that's just going to be an arc between our 2 deterministic nodes, and everything is just going to be nice and deterministic, but talking about kind of sets of the NFA's states. Okay, so one state of the DFA is going to correspond to a set of states of the NFA, and that's going to be the trick that's going to let us convert an NFA to a DFA, right? And then we have to worry about the accepting states of the DFA, right? And the state of the DFA is accepting if the set of states it corresponds to in the NFA contains an accept states as one of those accepting states. Okay, so, all right, so there's going to be a more formal version in the notes, but this is the gist of the construction of why we can convert an NFA to a DFA and vice versa. So now let's briefly talk about why we can convert a regular expression to an NFA and vice versa. So let's kind of do this NFA to regex. How do we do that? So first of all, to show that the NFAs can do anything a regular expression can do, we can first show that, okay, so we can define NFA for the starting states for the empty set, the set containing epsilon, and the set containing C for any C and sigma. It's not hard to just build DFAs for these even. You don't even need to build NFAs. Define DFAs for each of these base cases, basically, for the regular expression. And then show that NFA, you know, the languages of NFAs are closed under union, concat, and star. So we can show that if you already had two NFAs that can, one for language A, one for language B, then there's an NFA for their union, an NFA for their concatenation, and an NFA for their star. Okay, and that's not hard to do. You know, if you had two NFAs, like if this is NFA N1, or like NA, let's say, that recognizes language A, and this is NFA NB that recognizes language B. Okay, then you can sort of have a new start. We can add a new start state here, and we could put an epsilon transition here or here. That tells you can go for free, choose for free whether you want to go to the NFA for A or the NFA for B. Choose for free which one to go to this, and just go to the start states of those. And this new NFA is going to recognize A union B, right? It's going to accept a string if and only if either this NFA for A accepted it or the NFA for B accepted it, because you'll just take an epsilon transition for free at the beginning before reading the string. Okay, so that's kind of how you show it's closed under union. And you can similarly show that it's closed under concatenation and star, using similar tricks. And that's in the notes. And because of such tricks, then the NFA can clearly do an NFA can clearly do anything a regular expression could do, because a regular expression only starts from the base cases and then uses union, concatenation, and star. So the NFA, we can construct it by starting from these base cases and keep, you know, adding the union trick, the union construction, the concatenation construction, the star construction as needed to get a more and more complicated NFA until we get to our desired language for that regular expression. So if we have a regular expression for language, then we will have an NFA for it using this trick. What about the reverse? And so just very briefly, let's say that we have an NFA N, and then we have L of N equals A, and we want a regular expression. So this one is the trickiest conversion, perhaps. We introduced in the notes, we proved this by introducing the concept of RNFAs. RNFAs are kind of NFAs, and, you know, machines that are allowed to be labeled by, the arcs can be labeled by regular expressions themselves. So you can have transitions that are labeled by regular expressions. But otherwise they act like NFAs. So you're allowed to do this kind of, you're allowed to do things like this in an RNFA. So in an RNFA, you can have these arcs labeled by entire regular expression, and you're allowed to take a transition if you read a set of symbols that matches that regular expression, right? So if you start with 0, 1, 1, if you're reading this as input, then you can take this arc and have read 0, or you can take this arc having read 0, 1, or you can take this arc having read 0, 1, 1. So you can actually take this arc in multiple ways. You can take this arc and read either 0 or read 0, 1, or read 0, 1, 1. And in any of these cases, you go to Q1 and you have fewer things to read. You have some number of symbols to read, that depending on what you want, because those strings all match 0, 1 star. Okay, so anyway, you can define RNFAs. We define those in the notes. And then as soon as you define RNFAs, you can kind of see that you can remove states from an RNFA and just use make the additional arcs, kind of make the regular expressions more complicated and keep removing states subsequently. So if you have a state like this Q2, you can kind of delete it and create one arc that kind of corresponds to the paths that went through here. So if you had a way to go through Q2 and to get to Q1, then now you can add an arc that does it directly and is labeled by some regular expression. And then now you will have these duplicate arcs. You have to have two arcs from Q0 to Q1, and you can just merge them into one arc by taking a union of the regular expressions. So using that kind of trick, you can do a state elimination out of the RNFA. So you can take a complicated RNFA and continue simplify it until you have an RNFA that just looks like this. So you have a start state and you have an accept state at the end, and you only have two states. And here you have some regular expression R. And the regular expression will depend on the RNFA you started with. And you can always do this simplification. You can take an arbitrary NFA and kind of reduce it to some very simple form like this. And the notes will describe how. And once you do that, then it's clear that the set of strings that this very simple RNFA accepts is exactly the ones that match R. So it's exactly the language of R. So to convert an NFA into a regular expression, first we note that any NFA is by definition also an RNFA. RNFA is a generalization. So you take your NFA and then you keep doing these reductions where you remove states, and you get a more and more complicated RNFA that's simpler in the number of states, but more complicated in the regular expression, until you get this extreme version where it has only two states and only one regular expression in between them. And then this is the regular expression that generates the language of the NFA. So something like that. So it's kind of the subsequent simplification using this RNFA definition. Okay, so that was a bit vague and probably didn't make much sense in the video, but I just wanted to kind of give a rough sketch of how this conversion works. So this is kind of the main take-home message here from the first part of the course, is that all these definitions end up being giving rise to the same class of languages called the regular languages, and we will study them a bit more in the rest of the first quarter of the course, or the first unit of the course, to see which languages are regular and some of their nice properties.